This video is about the mathematics that applies to both oscillators and waves. Oscillator math are the equations that apply to any oscillating system. By using this approach, you can minimize the number of equations you need to learn and make your calculations simpler. Rather than using one equation that you'd grab for a particular problem, you use something specific to that problem and then apply the various oscillator math equations to connect that to the other things you might want to know. The reason this is important is that there are many different systems that oscillate. It could be the suspension system of a car, it could be a pendulum or a swaying building, or it could be a radio transmitter like we'll see when we get to the next semester of this course. Every one of these uses the same mathematics. They're periodic motion with a particular amplitude that results from a restoring force. If that restoring force is complicated, you'll get a complicated motion that repeats itself over time. If that restoring force is simple, you'll get simple motion. The important variables here are the frequency, which is measured in hertz, which is the number of oscillations per second, and the period, which is measured in seconds, which is the number of seconds per oscillation. One is just the reciprocal of the other. So if you know the frequency, it's reciprocal as the period. If you know the period, it's reciprocal as the frequency. Simple harmonic motion occurs whenever the force is simple, specifically when that force is a linear restoring force. In that case, the oscillation still has an amplitude, period, and frequency, but it's described by a sine or a cosine function. When you use a sine or a cosine function, you have to introduce an additional variable omega, whose role is to convert time into radians. The reason for this is if you plug in time, you have to convert it to radians before you can evaluate the cosine function of that argument. Omega is twice the pi times the frequency, or twice pi divided by the period. Notice that if you know frequency is 1 over the period, you can go from omega equals 2 pi f to omega equals 2 pi over the period by simply using that fact. Omega is the angular frequency in radians per second. It's related and similar to the angular velocity, also radians per second, that we discovered when we were studying circular motion. This really is because it's a property of the cosine function, not anything tied to the physics. Not only is there oscillator math, there's also rotation math, and they share this same set of relationships. Any system that oscillates will obey any combination of these equations that you might want to construct algebraically. I recommend learning omega equals 2 pi f because that's what I use the most specifically when we get to the second semester of this course. However, there's no reason why you can't learn frequency as omega over 2 pi or period as 2 pi over omega. What you shouldn't do is learn an equation that's got other things in it. You should learn this basic equation so that if you know omega, you can calculate the frequency or the period. If you know the frequency or period, you can take the reciprocal to get the other one. That reduces the number of equations you have to learn into a very simple set that you'll always use correctly when you need to use one of them. Omega is where the physics comes in. When we set up the differential equation from F equals ma, for example, ma equals negative kx for a linear restoring force of a mass on a spring, when we solve for a, which is the second derivative of x, we get negative k over m times the position. When we test our solution, we find that this requires that omega squared be that ratio k over m. That is, omega always is written in terms of simple things that appear in the differential equation. And since the differential equation comes from the physics equation for the forces and accelerations, it's always written in terms of things that are simple in terms of the input physics. Whatever force is applying will appear, and whatever mass is appearing will appear in the expression for omega. That's why I recommend learning the equation for omega separately and then using it in the oscillator math equations. The ones we'll use in this course are omega equals square root of k over m for a mass on a spring, and for a pendulum, it's square root of g over l. Notice it's always something related to the restoring force, some factor related to the restoring force, and some factor related to the inertia. That's the structure of all of the ones that you might encounter for oscillating systems. Wave math are the same concept. It's definitions and equations that apply to any traveling wave. Again, there's a minimum number of equations you need to learn. Some of them are the same as the oscillator equations. These apply to anything that waves. Oscillations of a string, like at a guitar or a piano. Oscillations of water wave, like surfing or a storm surge or a tidal wave, a tsunami. Or radio waves. These are traveling waves, which have to be written in terms of a special function of x minus vt. That gives you a wave that travels to the right at speed v. The function can be any shape that that wave might have. One convenient function for a pulse is what's called a Gaussian pulse, a times e to the minus u squared. That would be one way to describe a wave pulse that occurs when you, say, shake a string or a rope, or if you throw something into the water and you get a little wave pulse that flows across the surface of a lake. Any wave that repeats harmonically can be written in terms of sines or cosines. And again, here, we can't have an argument that depends on meters, like x minus vt is in units of meters, so we have to multiply it by a parameter k, which converts meters to radians, so that we can then evaluate the cosine function. This is a new factor that we're going to have that shows up in wave math. So, to repeat what I just said in another form, whether it's x minus vt or kx minus omega t, those are the most common forms we see. This is a pulse or a harmonic wave that's traveling to the right in the plus x direction as time increases as a result of that minus sign in the expression. The reason for this is something that you learned in college algebra. If you subtract a phase, you shift the function to the right. Subtracting a phase corresponds to shifting the function to the right. So this looks like a wave that travels to the right as time increases. It's an oscillation in time. The omega t says it oscillates with a frequency of 2 pi f equals omega, or a period 2 pi over t equals omega, where omega is again the angular frequency. It's oscillating in time just like an oscillator. In fact, that's how you create a wave, is to drive it with an oscillation in time. If we look at a fixed position on the string, it oscillates up and down, for example, as time progresses, and it has a period as shown here. It also oscillates in space. That's the part that's new for a traveling wave. That's described by the kx term, where k is 2 pi over the wavelength, and x to convert meters into radians. K is usually called the wave number, although you might learn a different term for that in some other course, depending on what particular profession you're in. Again, if we take a photograph at a fixed time, we'll see an oscillation in space, where that oscillation in space is described by the wavelength, which is called lambda, that Greek letter that you see in this expression. The wave travels at a speed. We can prove that that speed is omega over k, although we don't usually use that except when we're using the wave equation that you've seen here in the wave function that solves that wave equation. V is omega over k. What we use more often is that V is equal to the frequency times the wavelength. You get that by substituting what omega is in terms of frequency and what k is in terms of wavelength. And just solve, simplify, cancel out the 2 pi's, and V is f lambda. There's a minus or plus that I use in the wave equation, in the wave function that solves that wave equation, to indicate that the wave moves in the plus or minus I hat direction. That is, the top sign, that minus, goes along with the top sign plus for the direction of motion. Minus omega t means plus I hat motion. Plus omega t means negative I hat motion. And this is a convenient way to summarize that by writing the minus or plus to remind us that it's backwards from the direction of motion. Again, there are special cases for the velocity. If it's a string, the velocity is the square root of the tension divided by the mass per unit length. Sometimes that's called mu, sometimes it's called rho. I write it in this most general form so that it doesn't depend on what equations you happen to use, what symbols you happen to use for tension or mass per unit length. For sound, we'll just use numbers. That is, the velocity of the sound in air, we'll use the standard value of 343 meters per second. In this course, there are different numbers that depend on temperature. If you're doing an experiment in a particular laboratory, you need to know the temperature because the speed of sound depends significantly on temperature. In general, All waves are produced by, again, some kind of restoring force that ends up in the numerator, a tension for a string, and some inertia factor that is what limits the speed of the wave as a result of that tension and the acceleration the tension produces. In this case, mass per unit length is what applies to a string. Finally, I want to give a quick overview of one of the problem-solving techniques that we use for waves, specifically for standing waves. The developed step is to count either half or quarter waves. After you've done the counting, solve for lambda, then use v equals f lambda and the formula for v to figure out what you need to figure out in the problem. The unknown might be v, it might be f, it might be actually lambda, based on what you know in the problem. If the wave is on a string that's fixed at both ends, you count half wavelengths. 1 for that simple case there for the fundamental at the top, 3 for this case that's shown down below. You're basically counting the antinodes. That turns out to be the harmonic number, but the process is count the number of antinodes, count the number of half waves, and then solve 3 lambda by 2 equals L for lambda. Follow this procedure and you don't have to try to remember all sorts of complicated equations. Just draw a picture, look at it, count, and you can then do algebra from that point on to find what you need to know. If it's free at one end, what you see are fractional waves, quarter waves. So now we want to count the quarter waves. For the fundamental, there's 1 quarter wave in L. For this next case that's shown here, there's 3 quarter waves in L. And again, as before, if you count the quarter waves here, the number of quarter waves is the harmonic number. So what you see in that picture, 1, 2, 3 in that second case, means there's 3 quarter waves, which you can then solve to find lambda. It also means that it's the third harmonic of that system. As before, a quick credit page indicating that these figures all came originally, at least, from Wolfson's textbook.